Hello students, welcome to Vista's Learning. This is Shruti, your science tutor. As we all know, we are handling chemistry now, 11th standard, right? Yes students, here we have Vista's Learning which provides you the quality education for all. So, as we have already started with our classes, we are in the second chapter, Structure of an Atom. And here we have already started with the lecturing classes, and this is our 6th lecturing class. If you have missed any of the classes, you can get to the website, our website www.v-learning.in, and you can browse into the videos if you have missed. Yes, students, studies is very much important. Keep learning with Vista's Learning, and we'll get into the 11th standard chemistry with 2nd chapter and 6th lecturing class. Yes, what we are discussing in this session. Already we have started with the theories of the models of atom. How it is been increasing, or what is evolution of atomic structure the scientists have been giving. Now we are studying about the Bohr model of hydrogen atom. Here we are specifically saying that Bohr's model of hydrogen atom because later you'll understanding the limitations of Bohr's model, why we are just specifically saying about the hydrogen atom. Next we are studying about the mechanics. What mechanics is this? Quantum mechanics. As you know, mechanics, it comes with the motion of particles, right? Here, as we know, electrons are moving in the orbits, and that's why we get the introduction part of quantum mechanics, and also Heisenberg's uncertainty, which helps us to study more about the atomic model. So here, some of the postulates of Bohr's atomic model. What did he say? The electrons in the hydrogen atom move around the nucleus, and they have the circular path, which we also call it as fixed radius, and fixed energy is been present for that orbit, and those paths are called as orbits. The fixed orbits in which the electrons revolve around the nucleus is called as orbits, or we can also call it as stationary states or allowed energy states. The energy of an electron in the orbit is it doesn't change with time. If the time has been changed, it doesn't change. It is exactly fixed. The energy of an orbit will not change either for the time or any other things. The electron can move from one lower energy level to the higher energy level. That means what? As we all already know, if I have the nucleus, if this is a nucleus, and the first orbit which is near to the nucleus is called as lower energy level, and the one which is going apart will be having the higher energy level. That means if you see the atom, the nucleus around the atom, the first circle around that will be called as first orbit, and that will be having less radius. Whereas when I take the outermost one, it will be having longer radius from the nucleus, right? That will be having longer radius. From the lower to the longer radius, the width also changes, the circumference changes, right? So you can calculate like this. If you have the lower radius, then the energy will be less for the closest one. If the larger radius, energy will be more for that orbit. So we say this is the ground state, the least state or energy levels, as we say, we'll take it as E1 state or ground state. For the first state, which is nearest to the nucleus, is called as ground state or E1 state. From that, as we are seeing here, electron can move from a lower stationary state to the higher stationary state. That means electron can jump from first energy level to the higher energy level. It might be for the second one or third one or fourth one or for fifth one. It depends on what energy it is absorbing or what it is emitting out. Fine. So electron can move from one and like lower stationary state to the higher stationary state when required amount of energy is absorbed by the electron which is present in the ground state. If it is not getting any energy, then it cannot excite or it cannot jump to the higher energy level. Hope you understand this. Good. The next point is that the energy is being emitted when the same electrons will come back to the lower energy level. That means, as I said, if this is the third, second and first orbit respectively, then if the electron is already excited, it is in third energy level. When it is coming back, it emits the energy what it has already absorbed while exciting. So that energy will be given out or emitted out. The energy change does not take place in continuous manner. As I've already told about electromagnetic radiations, when you get the radiations or energy which is emitted out, that will not be in a continuous manner. Instead, it will be in a line spectrum. The frequency of radiation, that means the energy which is being given out is having certain frequency. As we know, E is equals to h mu. So the energy is associated with the mu. Mu means frequency. So the frequency of radiation which is absorbed or emitted when transition occurs will be given by mu is equals to delta E by h. Why we take this delta E by h? You can see E is equal to h mu, we know, right? Yes, students. So if I take E is equals to h mu, then you can understand this delta E why we are taking. That means if this is the third and this is the second excited state or ground like energy levels, electron is coming from third to second, then the energy level of third we can count it as E3, for second one E2. The energy possessed on that orbit is called as E2 and E1. Likewise, you can also take E1. Okay, so here we are taking E2 and E1. Excuse me. So you can take energy electron coming from E2 to E1. So when it is coming from second orbit to the first orbit, the certain energy is emitted out. That energy we are calculating in terms of mu. As we know, they are directly proportional. Energy is directly proportional to mu. So what happens? Here instead of E, we are taking the difference between E, E2 and E1. So that E2 minus E1 will be given as delta E. That is where mu is equals to delta E by h. Why by h? Because we know that E is equals to h mu. So if I want mu, I can transfer E by h. Like h I can transfer and I'll get E by h. So mu is equals to E by h. But as we know, it is the difference between the higher energy level to the lower energy level. So we'll be having delta E by h. Hence we get E2 minus E1 by h. So here as we know, E1 is the lower energy level and E2 is the higher energy level. And here this expression is commonly called as Bohr's frequency rule. What do we call it as? We call it as Bohr's frequency rule. Is it fine? Yes. Next we have this where the angular momentum, as any of the object is moving in a circular region, then the angular frequency or angular momentum will be there. So here we are calculating the angular momentum, and in physics you might have studied it will be given by mvr, where m stands for mass, v stands for the velocity of the object, and r for the radius in which the circular path it is moving. So here we are taking m E because it is the mass of an electron. So here we get the angular momentum for the integral multiple. What is this integral multiple? This angular momentum is the integral multiple of h by 2 pi. Integral means the integer will be like multiplying. If you multiply 1, it gives the first orbit, 2 second orbit, 3 third orbit. So it will be the integral multiple of h by 2 pi, where n is equals to 1, 2, 3, as I said, the number of orbits. The stationary states of electrons are the number as n is equals to 1, 2, 3, 4, as we discussed KLMN. So the first one, which is near to the nucleus, will be called as 1, and successively we will be calling it as 2, 3, and so on. And these orbits will be given as a principal quantum number. We'll study in detail of this principal quantum number in quantum mechanics. So the radii of the stationary orbits, the radius, for example, we always write this is the orbit, right? What is the radius of this? How to calculate? Can we calculate this? So if we have a doubt, we can calculate that by using this formula. So the radii of the stationary states, like stationary energy levels, can be expressed by Rn is equals to n square a naught. What is n square? As I said, it is a principal quantum number, whereas a naught is 52.9 picometer. So what is this 52.9 picometer? You can easily find out. This will give you the first stationary state, which we also call it as Bohr's orbit. Next we have, as n increases, the orbits increases, the value of R also increases. So obviously, yes, if the number of concentric circles are increasing, the distance from the nucleus to the circle will increase. So by that, the radius increases. As radius increases, as I already said to you, the energy of the orbit also increases. That is what they are mentioned here. So energy of an electron is given by, if we have that energy, then how it will be given? We have En is equals to minus RH. As we already know this, RH is the Rydberg's constant into 1 by n square. 1 by n square. N is again a principal quantum number which refers to the number of stationary states, where n is equals to 1, 2, 3 and so on, and where R is equals to, see students, R, it is in energy, joules. So it will be 2.18 into 10 raised to minus 18 joules. So next we'll just discuss how this E will be given, okay? So if you take E is equals to R H. RH means it is been given by the Rydberg's constant. That is given for hydrogen, right? 1 by n to n square. For other hydrogen-like atoms, how to derive it? Because hydrogen-like atoms will not have same number of protons and electrons like hydrogen. So how do you calculate the energy levels for hydrogen-like atoms? For example, hydrogen will be having 1 electron, 1 proton. If you take helium, it will be having 2 electrons, 2 protons. So this is exactly different from hydrogen. If I want this helium to be the hydrogen-like atom, then I need to remove 1 electron and I should have 1 electron. And also, if I remove 1 electron, it will not be changing its proton. The number of protons will be same. So what can I do with this? So we say hydrogen-like ions, where they only have 1 electron in the outermost shell. Likewise, lithium Li plus 2 will also have 1 electron, but it will be having different number of protons, like 3 protons it will be having. So the mass, like atomic mass, just change for other atom like hydrogen-like ions. So for them, how to derive the energy level, we'll check it now. So if you see E, is equals to the Rydberg constant 2.18 into 10 raised to minus 18 joules into, we need to take in the bracket, what we have to take here, 1 by n1 square, right? So here instead of 1, we are taking z square by n square. Why we are taking z square here? As I said, we have the different mass number. So Z has the different mass number for helium, lithium, beryllium, likewise. So you can substitute that and derive the energy level. So next we'll be having this for N. Why we are taking N? Because which orbit we require, that orbit energy we can derive it. And here while deriving, we need to know about one more. En is equals to RH by n square. Why we are taking En is equals to RH by 1 square here? This is for hydrogen atom, because Z is 1 for hydrogen, 1 square is 1. So we get, instead of RH into 1 by n square, we can directly write En is equals to RH by n square. Is it clear, students? Fine. Now as we are checking it out, delta E is equals to what? Delta E means the energy difference between higher energy level to the lower energy level. So delta E is equals to EF, the final energy level, to the EI. EF minus EI. EF is the final energy level. EI is the initial energy level. So for this, if you substitute the value of E, you will get RH divided by n square minus, here you need to know NF, we need to mention, not only N, because this is for final energy, that means final orbit. So orbit changes means here this is, for example, E2 minus E1, so it will become N2, okay, likewise N1. So we'll have RH divided by Ni square. So that gives you delta E, the energy difference between the final to the lowest. So what is common here? How can you remove this? And you need to also know, students, this is negative part. Why negative part? Because when it is coming from higher energy level to the lower energy level, the energy is given out. When we are losing energy, it is a negative form. So we are writing negative form of RH by N1 square. Okay. Is it clear, students? Fine. Now you have to remove this, the common out. As we know here, like RH divided by NF square, minus into minus, plus RH by Ni square. So if you see this, this is positive, this is negative. So we can write this delta E is equals to, here I'll take this first and then, because positive, negative, you can just take it like this, positive RH by Ni square minus, why? Because this is having minus here. So RH by NF square. So delta E is equals to, now I can take common out. So RH into 1 by Ni square minus 1 by NF square. So this is how we get. So is it clear, students? Do you have any doubt with this? So what is the value of R here? As we know in the last slide, we have taken R is equals to 2.18 into 10 raised to minus 18 joules into 1 by Ni square minus 1 by NF square. Is it clear? Any doubts? So this is about the energy difference where you can get from this formula. Understood? Now we'll check with the mu, the frequency. We know the relationship between delta E and mu. So mu is equals to delta E by h, where h is the Planck's constant 6.626 into 10 raised to 34. So here we can get that back here. As I said, delta E is equals to 2.18 into 10 raised to minus 18 joules into 1 by Ni square minus 1 by Nf square. Right? So now, as I said, we are going with this. E is equals to h mu. So mu is equals to E by h. So I want to find out the frequency of radiated energy. So mu is equals to delta E by h, and that I can take this divided by h. So 2.18 into 10 raised to minus 18 joules divided by 6.626 into 10 raised to 34 into 1 by Ni square minus 1 by Nf square. Are you getting this point? Do you have any doubt? Fine. So next we have to calculate about 2.18 into 10 raised to minus 18 divided by 6.626 into 10 raised to 34. What do we get there? So we get around 3.29 into 10 raised to 15 into 1 divided by Ni square minus 1 divided by Nf square. Do you understand this? It is Nf square. Is it fine, students? Any doubts over here? Fine. So next we have the mu bar. We need to find out about the mu bar. As we know, mu bar is equals to, how to find out the mu bar? This is when we have mu, okay? To find out the frequency, then we have this value. For finding out the energy, we have to take this formula. Okay, fine. Now we are checking with mu bar. What is this mu bar? As we know, mu bar is equals to 1 by lambda. Lambda is the wavelength and reciprocal of wavelength is called as mu bar or wave number. So how do you get with this connected with the mu? So we have the equation mu is equals to C by lambda. Right, students? This we have got. So mu is equals to C into mu bar, because 1 by lambda is equals to mu bar. Good. So mu bar is equals to, we have mu there divided by C. As we know, mu is equals to mu bar into C. Now you will get mu is like mu bar is equals to mu by C. Is it clear, students? Hope you are understanding here. Yes. So now we have mu bar is equals to, so mu bar is equals to mu by C. So what is mu? We saw that mu is equals to 3.29 into 10 raised to 15 into 1 by Ni square minus 1 by Nf square. Right? Thus, divided by c. What is c? C is the speed of or velocity of light. So that also we have studied in your first basic concepts of chemistry. Do you remember that? That is equals to 3 into 10 raised to 8 meter per second. So on calculation of this, you will get around 1.09677 as a number. So with this, we'll be having into 10 raised to minus 7. Are you getting this? That into 1 by Ni square minus 1 by Nf square meters. As I say, this meter comes on the numerator, we get meter. Okay. So hope you understand this, students. So we have mu bar is equals to 1.09677 into 10 raised to minus 7 into 1 by Ni square minus 1 by Nf square meter. Got this? This is the wave number which we can see here. Any doubts here? Just a while. So here it is 15 sprints 10 raised to 15 and this is 8. When this comes to the numerator, it becomes 15 minus 8. So 15 minus 8 is plus 7. So I have written here minus 7, right? So it should be plus 7. Hope you understand this. Good. So this is how we have the delta E to derive and mu bar and mu. Hope you understand this, students. Any doubts? You can just comment. So next, when electron is free from the influence of nucleus, so the energy is taken as 0. So here we have the attraction between the nucleus and the electron. If there is no attraction from the nucleus, then the energy of this electron will be equal to 0. That is what they are mentioning here. So Bohr's theory, as we can see there, it has been applied to the ions containing only one electron. As I said, helium, lithium ions, if they have one electron, and that is applicable for those hydrogen-like ions. You should not say hydrogen-like atoms because they have positive charge on them by losing of electrons. So we should mention them as ions. Okay? They are ions which are hydrogen-like atoms. Is it correct? If I say hydrogen-like atoms, then this will become helium without any plus charge and lithium, beryllium. They will be having 3 and 4 electrons as usual. Now tell me, will it be equal to hydrogen-like atoms? No. You should say hydrogen-like ions or ions containing one electron which are similar to that of electronic configuration of hydrogen. And these energies of stationary states associate with the similar kind of ions. As I say, you can also take this for similar kind of hydrogen atoms, but you should remember that Z square is important here. The Z changes for helium, neon and beryllium, where it is 1 for hydrogen. So here you have the equation where the energy level gives you the energy of the stationary states will be given as En is equals to minus 2.18 into 10 raised to minus 18 into Z square by N square. As I said, Z is the atomic mass of the hydrogen-like species and N square or N resembles the number of orbit. So and the radius, as we can give this with Rn is equals to 52.9 divided by Z into N square. It is easy to derive, as we saw the Rn is equals to 52.9. Okay. From this you can find out, if you know the atom or atomic number of the given element, and also with the Z, like n, the orbit, which orbit the electron is present. From that you can easily find out the radius of the orbit. Next we are discussing about, as the atomic number increases, this atomic number increases means, for example, hydrogen, it is 1. For helium, it is 2. Lithium, it is 3. Beryllium, it is 4. Boron, it is 5. Carbon, it is 6. So, if you see here, the number of atomic number or Z is been increasing. As the Z increases, the radius decreases. For example, if I take the first orbit of hydrogen, hydrogen has 1 proton inside, 1 electron inside. So it will be having this radius. Okay. If I consider the helium, and it will be having the same radius with 2 electrons. This is how we think, right? But it is not. The size of the hydrogen first orbit, K shell, will be larger than that of the helium, that is K shell itself. Why? Because here in helium they have 2 protons, in hydrogen they have only 1 proton. So nucleus which is attracting that orbit in hydrogen is less compared to that of helium. So here twice it is attracting more. When someone is attracting more, then the distance between them decreases, right? So similarly, from hydrogen to helium, the radius decreases. That is what we are saying. As the atomic number increases, number of electrons are increasing, then the size also decreases, the orbit also decreases, the radius decreases, and also the energy becomes negative. Why the energy becomes negative? Because it is decreasing, right? So energy present in that also decreases. So electrons will be tightly bound with the nucleus, as we know. The magnitude of the velocity of electron increases with increase of positive charge on the nucleus. If you have more positive charge inside the nucleus, then the velocity of the electron increases. By this, I'll ask the question, if you have hydrogen and helium and they both have K shell, that means only one shell, the electron in hydrogen and electrons in helium, which will be more velocity, which will be having more velocity, because they both are in same orbit, K shell, right? Here, the electron in hydrogen will be having less velocity than that of helium, because the positive charge on the nucleus here is +2, where in nucleus it is +1. Understood? So the positive charge, that means protons present in the nucleus, also matters for the velocity of the electrons revolving around the nucleus. With the increase of principal quantum number, as the quantum number increases, then they decreases, the velocity decreases. What does this mean? That means if I take lithium, the K shell I have, K shell is having 2 electrons in lithium and L shell have 1 electron, okay? Now, the velocity of this L shell, the electron present in the L shell, will be obviously less than that of hydrogen or electrons present in the hydrogen K shell. Why? Because the N shell is been increasing, the principal quantum number is increasing. For K it is 1, for L it is 2. As the orbits are increasing, the electrons present in that orbit will have lower velocity. Understood? But you need to remember they have the higher energy level state. So next, as we are discussing here, we have in case of this. Okay, do you understand this students? Yes. In case of absorption spectrum, like when the electron is being absorbed, what happens with the NF and NI? That means when you have to get the absorption spectra, then the NF should be greater than that of NI. NF is the state where the electron is moving. If I have the electron in the ground state, then this is the NI, initial ground state, right? Initial energy level. NF is this final energy level. So, if you have NI greater than NF, then that will undergo the emission spectrum. I'll just show you. If this is NF and this is NI. So, this is the first condition, this is the second condition. In first condition, the NI is least and NF is more. So, it is jumping from lower to higher energy level. While it is jumping, the energy level, like energy is absorbed and then you are getting the excitation. So, here the energy is absorbed. And hence, we get absorption spectrum. You need to remember, when do we get the absorption spectrum? When Ni is lesser than that of NF. Now, I'll say Ni is in the higher energy level and electron is there. And this is the initial state where an electron is there and it is coming to the final state. So, here it is coming down or it is lowered. So, when from higher energy level to the lower energy level it is coming down, it liberates the energy or it emits the energy, and that energy will be given as emission spectrum. I repeat, in absorption spectrum, Ni should be lesser than NF and the energy is absorbed here. So, you can see energy will be absorbed by the electron and that delta E is equals to positive. Why it is? Because NF minus Ni will be given by delta E, which will be equal to positive. So, we can say if you have the absorption spectrum, delta E will be equal to positive. Whereas for emission spectrum, as this is the emission spectrum, here Ni should be greater than that of NF and the energy which is being emitted or delta E is taken as negative because we are emitting the energy. When we are losing the energy, obviously it will be negative. When we are gaining the energy, then it will be positive. Fine. So, each spectral line, whether absorption or emission spectrum, can be associated with particular transition in hydrogen atom. That is obviously correct because either it is coming from higher energy level to the lower energy level or lower energy level to the higher energy level. Each transition of electron jumping from higher to lower or vice versa will be having the transition in hydrogen atom, and we can notice that. In case of large number of hydrogen atoms, if I take more number of hydrogen atoms, then what happens? Each hydrogen has its own electrons and all the electrons will be absorbing energy and exciting. So, transition will be continuously occurring and then it will be very difficult for us to see the transition, how it will be formed. So, transition can be observed. It will be very difficult for us to see, and different possible transitions are occurring when you take more number of hydrogen atoms. That leads to the large number of spectral lines. Intensity of spectral lines depends on the number of photons which are striking the electron. That means the number of photons, as we know, photons is given by h mu. One energy is equals to one packet of energy, actually what we say, that will be equal to h mu, and that one will be called as photon, and it depends on number of photons which is falling on the electron for the intensity of spectral lines. Okay, and also if you have same wavelength of photons, you should remember the number of photons are mattering for intensity of the spectral lines either in absorption or emission spectrum. Now we'll just check with the problem. What are the frequency and wavelength of photon emitted during the transition of n is equals to 5? That is the fifth state, the fifth orbit, and to the second, like n is equals to 2 state in the hydrogen atom. As you can see here, we have n is equals to 5. That means 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5. The electron is in fifth energy level. It is jumping to the first energy level. That means it is coming to the second energy level. As we have already studied about the hydrogen spectrum, the first, if Ni of the electron is coming to the first, we call it as Lyman. For the second, we call it as Balmer. For third, Paschen, bracket, Pfund, right? Likewise, for this, N is equals to 2. That means this is the initial Ni. Ni is equals to 2. So we can say it is a Balmer series. And Nf is equals to 5 here. So delta E, as we saw in the previous derivation, delta E is equals to 2.18 into 10 raised to minus 18 joules into Z square by, or else you can take it as 1 by N F square minus 1 by Nf square minus 1 by N I square. Why we are taking 1 by way, the Z is not been taken here? Because it is for hydrogen atom. As we know, for hydrogen atom, Z is equals to 1, 1 square is 1. So we'll be having here 1 by 5 square minus 1 by 2 square, where we get the answer as delta E is equals to minus 4.58 into 10 raised to minus 19 joules. When we get this minus, you should understand that this is the emission spectrum. As I said, it is coming from higher energy level to the lower energy level. The energy is being radiated out, and from this negative sign you can understand that it is an emission spectrum. Next problem. What are the frequency and wavelength of the photon emitted? This we did, right? Yes. So here we just saw about the energy. Now we have to check with the frequency, because they didn't ask about the energy, but we need to know the frequency and wavelength. To know the frequency and wavelength, we need to know energy. So energy we got to know, and frequency is equals to what? Frequency is equals to delta E by H. So delta V, just now we got minus 4.58 into 10 raised to minus 19 joules divided by H. What is the H? Planck's constant 6.626 into 10 raised to minus 34 joules per second. So here the joules get cancelled, and for frequency we have the hertz, which is the unit. So we got it as 6.91 into 10 raised to 14 hertz. This is the mu frequency. Now once we know the mu, we can find out the wavelength, because wavelength is lambda, mu is frequency. How they are related? Mu is equals to reciprocal of lambda. So if I take lambda is equals to 1 by mu, then I get the lambda over here. Right, students? Yes. So wavelength, that is represented by lambda, that will be equal to C by mu. Why will take C by mu? Because 1 by lambda will be given as mu bar, where C by lambda will be given by mu. So we are taking C by mu, that is equals to 3 into 10 raised to 8 meter per second divided by 6.191 into 10 raised to 14 hertz, which gives you 434 nanometer. What is this nanometer? 10 raised to minus 9 is given as nanometer. Next question. Calculate the energy which is been associated with the first orbit of helium. What is the radius of this orbit? So if you have the helium, they have given +1. Got it? It is hydrogen-like ion, and for this, the first orbit and its radius, the energy of this first orbit and the radius of this Rn, we need to find it out. So, En is equals to, as we know, minus 2.18 into 10 raised to minus 19 Z square. Why Z square? Because it is not hydrogen, it is helium. So, Z square divided by N square we get here, and that N square is the orbit. Which orbit they are asking? The first orbit. So, N will be 1. When you substitute N is equals to 1 and Z is equals to 2, because 2 is the atomic number of helium, then you will get the answer as minus 8.72 into 10 raised to 18 joules. This is the energy associated with the first orbit of helium. What is the radius? Radius, as we know, it is been given by Rn is equals to 0.0529 nanometer into N square by Z. What is this N square? As I said, N is the 1, Z is equals to 2, and here we get the answer as 0.02645 nanometer. This is the radius of the given first orbit of helium. Understood? Fine. So now we'll just get into this Bohr's model. What the Bohr's model of hydrogen has improved. Like, yes, it has the improvements than that of the Rutherford, but it also has some disables, or it have demerits. We'll speak about that. But previously, we'll just know what the Bohr has difference with the Rutherford nuclear model. Rutherford said that the atom is having positive charge and electrons are revolving. He didn't explain the stability of electrons are revolving around the nucleus. He didn't speak about the stability of an atom, and also he didn't speak about the hydrogen spectrum. But that was given by Bohr's model. What did the Bohr account? He also said the stability of, how does the stability? It has a specific orbit, and it is the electron is exactly revolving in that fixed orbits. Okay, fixed path, which we also call it as orbits. And the Bohr also explained about the line spectra of hydrogen. As the electrons absorb energy and they move, will be getting the line spectra of hydrogen. And also he explained with the hydrogen like ions. This is the postulate we can say. Whereas the demerits or limitations of Bohr or the Bohr's model, what he didn't explain. Here we have the Bohr, he fails to explain or to have a count for the finer details of the hydrogen atom. As we say, the electron which is jumping to the first orbit, n is equals to 1. Here, this again have the small portions. For example, if I take Balmer, it will be having small lines which is been splitting. That was not explained by the Bohr. And so, we say that is the limitation of Bohr. With that, he didn't explain about the other atoms than the hydrogen like atoms. Other atoms also we have, like carbon we have, nitrogen and the higher atoms, that was not explained by Bohr. Only he explained which are similar to that of hydrogen atom. And the splitting of spectral lines, as we know, it will be having 3 splits. For example, if you take the orbits in the orbit, if this is a K shell, or we also call it as K orbit, in this we have orbitals which is been represented by S, P, D, F, and those are not explained by the Bohr. That we'll study in quantum mechanics. Before that, what is Zeeman effect and Stark effect you need to know. So what happens here in Zeeman effect is that if I take the S and P orbit, for example, second K shell will be having S orbit and P orbit. So S orbit, either on the magnetic field or not, it will be having only one orbit. Okay. So here you can just have one orbit on applying of magnetic field. This is in absence of magnetic field. Absence, okay. If we apply the presence of magnetic field, I'll just take an example of p orbital that will be split into 3 different levels. So this splitting of p orbital into 3 levels was not explained by the Bohr, and that effect is also called as Zeeman effect, and we have the splitting of effect of like splitting of layers, which also have the shark effect. The shark and the Zeeman effect was not explained by Bohr, and so these are the limitations of Bohr model. And he explained about the ability of atom to form the molecules. Did he explain that? He didn't explain about how the molecules are being formed. They are being chemically combined, right? They have the bonds, we know that. For example, if I have one hydrogen, another hydrogen, they share the electrons and they have a bond between them. Like we have different types of bond, ionic bond, coordinate bond, like a covalent bond. That is not been explained by the Bohr how the molecules are being made. Got it? So these are the main demerits of the Bohr's atomic model. So he didn't again explain about the features, salient features of the structure of complex atoms. As I said, the higher atoms he didn't explain. Next we have the behavior, like dual behavior of matter. Like here we have de Broglie, the next scientist, who explains about not only the electrons, not only the rays, radiations have the dual behavior, even the matter, complete matter have this dual behavior. In 1924, de Broglie proposed that matter also have the radiation where it exhibits dual behavior. It also have particle nature as well as radiation nature. The photon has momentum as well as the wavelength. As we speak about photon are the particles which carry the energy. They also have the wavelength. Electrons should also have momentum as well as wavelength. Because electrons are subatomic particles, they also exhibit the particle nature as well as wave nature. This is what given by de Broglie, and he have his own equation which is being given by lambda is equals to h by mv. mv is nothing but mass into velocity. In physics it will be called as momentum. So we take it as lambda is equals to h by p, that is equals to Planck's constant divided by momentum. So de Broglie's prediction was confirmed experimentally when it was found an electron beam undergoes diffraction and interference. Like wave characters was being found by the electron beam. We know the electron beam, right? So a series of electrons are left and we are studying on that, and hence we can understand the nature of this characteristic nature of wave of electrons. We also studied the cathode ray tube, and there the particle nature we studied, and these electron beam also undergoes diffraction which is being given by waves. And an electron microscope is being used here, where a powerful tool to utilize or to understand the small structures of small microscopic elements or atoms. So that if you take, it will be 15 million times you can magnify the given substance and look through that. So using electron microscope we can also find out the structure of atom, the structure of other things. And here every object in motion has wave functions. So wavelength associated with ordinary objects are also short, and also they also have this wave properties which is not been exactly detected. So next we have the uncertainty principle. This will be studying in the next session, students. So I hope you all understood this. Yes, students. So by this we are almost ending this session. And if you have any doubts, you can comment us. And if you have not gone through any of our previous videos, if you have any doubts, you can log into our web application www.v-learning.in. Thank you, students. Keep learning with Vista's Learning.